All right. Well, this is where we were supposed to be, and in the robotics lab we have a lot of different robots. Especially we have Ocean One. I'll be showing you about Ocean One a little bit, but one of the important theme in our work is how we can bring human and robot to interact in different environments, in extreme environment, in medical environment, and in the workplace. And this is something that we have been doing, and we are going to see live here. So we brought a haptic device, and the haptic device is going to allow us to control a robot remotely from here to, a nearby building. In fact, we use the same system to control robot in Asia, 10,000 kilometers from here. And the reason is we are going over the internet. So the internet, wherever the internet is going to reach, we will be able to reach it. However, I have to distinguish between this sort of interaction and many of the interaction we heard about that more resemble like a connection on Zoom. That is, you see an image and you can interact visually without making contact. Well, here we have a haptic device, and we're going to be able to touch and feel and operate. We're going to do ultrasound imaging. We're going to do all kind of repair tasks for construction on tall buildings. We are going to be able to do that remotely because we are going to touch. And haptics is about the sense of touch, and we are using that to connect. So this is really a new way of approaching the problem of working in unstructured environment. This is very, very relevant to I mean, many aspects of the work coming in civil engineering. So,
Ocean 1K, a unique underwater robot capable of carrying out archaeological excavations several hundred meters beneath the sea. Since 2015, an American team has been developing this revolutionary humanoid. The objective is to be able to explore shipwrecks, handle relics, evaluate and study treasures with the same precision as archaeologists.
today, robots are designed to see, but we need robots that are designed to do.
After its first trials in 2016, Ocean One is about to make its first deep-sea dive.
We're in position, hold steady.
Can you handle the winch and the launch? After the descent, I can take over from the computer.
Okay, let's go.
In the course of 5 dives in the Mediterranean, Ocean 1K will be pushed to its limits and attempt to reach a depth of 850 meters.
I cannot go down enough.
Proceed with the first 4-meter movement. Stand by.
Same here.
This record would enable archaeologists to excavate countless wrecks of warships, merchant ships, aircraft, and submarines from every era that have up until now been totally inaccessible. But how can we be sure that Ocean One will withstand the extreme pressures? Or that its bionic hands will be able to recover sunken objects from the abyss?
Well, this is the trailer of a film about Ocean One. A film that was shown all over the world, in France, Italy, in US, and in Japan, and receiving a lot of awards. This film is telling the story about the expedition we had in 22 in the Mediterranean that took the robot from 40 meters all the way to 1,000 meters. This is 1,000 meters is really nothing for the oceans, you can keep going to 10,000 meters. But the thing is, we built a robot that is capable of returning the contact information to the operator. And we can feel what the robot is doing at those depths. In fact, in last September, almost a year ago, in Dubai, we took the robot to deep dive, and deep dive is an incredible place for a robot like this to play, because it has a sunken city with all kind of environment that is very rich for a robot to interact with. And you can see also the robot from outside, so it's transparent, and you can see the haptic devices connected to the right hand and left hand of the robot. We are wearing glasses so we can see in stereo. So we can see through the eyes of the robot, and we can touch through the hands of the robot. So basically you have an avatar. And when you move in the environment, you are able to interact with that environment remotely. So the robot was doing a lot of tasks, including cleaning, but also robots needs to have fun. So the robot was playing pool and winning. So let me just show you a little bit of that event that took place in September 27th. We're going to celebrate maybe next week 1 year of the 1 year anniversary of Ocean One at Deep Dive. So here is Deep Dive. My students are ready, and the robot is already in the water, coming. So we slide the robot, and then we separate from the vehicle, and the robot will start floating, and then it will go and swim. So this is was attended by many people, including the Minister of AI and many other dignitaries from Dubai. And you can see the Minister of AI taking photos of the robot. But what we're going to see first is the view from the eyes of the robot. So the robot is looking at us, and you can see two images, left and right. When we merge them together, we get the depth. And this is the stereo image that is returned to us and deployed and displaced for us to create that image. So now the robot is visiting an apartment at 30 meters, and we are projecting this on the top at 10 meters where we have the conference room, and interacting with the robot while the robot is at 30 meters. So deep dive is not about only the depth. It's the deepest pool in the world, but still what is this space is full of artifacts that allow the robot to create interaction, and there are also divers who go there. Now the robot found a diver, and they're trying to interact with the diver. I don't know, he thought to take the hand. So now we're going to play a little more, and the robot is going to do basket. Not easy to play basketball in the water. It's really tough. So we fill the basket with water so it stays there. And with the stereo, we are able to see exactly where to place the ball. Now the robot is doing a task of support to removal of this hose. And cleaning a table again. So underwater in the sea, ocean is very difficult because you have all the current. Here it is much better and easier. We have precision to play chess and win. And the robot is now interacting with itself in a mirror. So then the robot will interact with the public and create like motion similar to what people are asking for. And you can see the haptic device controlling and attached to the hands of the robot and creating that interaction. So this robot is, as I said, very different from many of the ROVs built for underwater exploration. These have cameras that would allow us to see what's going on, but not really to do or intervene. And any operation underwater requires touch, and removal of the object requires dexterous manipulation. This is done very often by a human wearing, inside suits. And these things works for 100 meters, 150 meters, but this doesn't at all solve the problem of exploring the oceans. Human cannot be in the ocean beyond about maybe 160 meters, 200 meters, when we start mixing oxygen with helium and other gases, but then this is not possible because humans will stay very, very short time. So the concept here is to create a way where we have two arms, because manipulation in unstructured environments requires two arms. If you put one arm behind you, you cannot brace, you cannot hold the object from the other side. And you really need to see your hand when you are manipulating. So you need to see the depth. So you need a head with a stereo vision. And this is something that we developed over the years with real-time simulation. This is a system that we developed that allows us not only to simulate movement, but also to simulate contact. So we can grasp object and feel the grasp and feel the weight of the object and move in that environment, sort of like a flight simulator, but now it's for the ocean. Now, this is the simulator system. It's very simple, very easy. In fact, people would come and within a few minutes, they can learn how to use it and interact with it. And this is true not only for this robot. This robot also is here, the system displaying the characteristics of dynamics, showing how we have to be careful about the posture of the robot so we will not create large impact forces. The robot was designed and built finally and tested here in the pool, and then the students will sit by the pool watching the robot, sometimes swimming with the robot. And then we took it to La Lune, to the Mediterranean, near Toulon, to a vessel of King Louis XIV, sunk off the coast of France in 1664. And this is our boat, L'André Malraux. And at 91 meters, we recover a beautiful vase from 1664. And that was a big, big event in France. In fact, there was a conference on archaeology, and at the press conference, all the media in France came, and that was April 30th, 2016. Well, this robot was designed to go to 100 meters, but we decided we really needed to build the next generation that will take us to 1,000 meters, and this is the robot that we will see today. Now, this is not really about archaeology only. I mean, archaeology is one important aspect, especially today with all the damage being done to the deep sea, looking for more and more fishing at the depth. And scientists need support when they are exploring the environment underwater. We were supporting scientists at the Colombo line for that volcano in Santorini the year after. But we have been working with oil and gas, exploring how we can serve and help with inspection, with maintenance operation underwater for all the human infrastructure that we have built. Inspection is very important, but also maintenance is critical, and you need hands, you need force feedback, you need those operations. We're also working with different groups on aspect of marine biology and how robots like this one can help with the plastic. This is a project with Abu Dhabi where they are putting a lot of emphasis on how to clear the seas from those large debris everywhere with plastics. Now, this is not only for underwater. I mean, the concept we're talking about is not only for robot underwater. We are doing a lot of different applications, including, as I mentioned earlier, interacting remotely with the robot that are doing medical tests at a distance. In villages, we can place in a small clinic a very simple device like the one you see here on the right, and a technician can run that general test, and then if we detect any problem with the test, then we can connect that patient to a hospital within 10,000 miles. Any hospital within 10,000 miles can be connected haptically to further examine and make sure that the patient is fine. So this is what Adrian, sitting here, is going to show us. I believe Adrian is going to start by showing us some repair on the top of the building, or where are we going to start? So to do that, I'm going to give you this, and you can connect it directly to your laptop. You go ahead. So the robot is in the Gates building, and we are going to interact with the robot from here. So you can see the robot over there. I see the robot over the phantom of a torso of a human. And we have also another structure on the left where the robot will also be operating. Yeah. So the interesting thing is from here we connect this same haptic device to any robot or to multiple robots. We're just sending command to IP addresses. And now we're going to, you can see the robot is, which one you're using? Okay, all right. So first we're going to do an ultrasound scan, and we're going to see the image on the left. Okay. Someone need to tap the screen from there. Do you want me to call him? Call him. The screen is frozen. Okay, well, then why don't you call him? So we're going to call someone to unfroze the screen. Yeah, it is there. The screen is working now. So when the robot is moving to the contact, then we can see the image. And this image depends on the amount of pressure, the angle. So would you like to tell us what's
Oh, yeah, we're just looking inside the abdomen here. It's filled with different organs, the same ones that we have, the right shape, right size, and all that. Right now we're looking at the liver, and they've planted in this torso some problems that I can see. Oh, let me, it has to restart.
Okay, so did you detect any problem with, could you show us where the problem is? So the problem is the fact that there are these white circles, and the white circles show high density tissues, and this could be cancerous. Okay, don't worry. Why don't you continue with continue with the other until he get it. So now we're going to go to a building and to remove some bolts, and okay, you can. Oh, there are some things to remove also from that structure. Could you take the brush? All right, and I can going. What is happening? It is with the workspace that is limited. So every time the robot doesn't advance, you go to the mid-range and restart centering the haptic device. So could you remove the, oh, what, already removed it? Okay, all right, let's, oh, wow. So now to place it, he's going to touch and feel the way approaching and put it down. I think we can applaud Adrian. Bravo. So Adrian just get another call from Amazon, and you know, they have a large data center, and at the data center they had a problem with one of the connectors. And you can see the connector over there. So could we go and remove this connector, the one on the left? Do you prefer the one on the right first? Okay, why don't you remove the one that you like? Yeah. That is fine. You're not reaching the haptic device, is that? Okay, now you're almost centered. You have to move to the right. So the setup is talking to the robot, getting the data from the robot about its position and about the orientation, and at the same time you are seeing the image. And bravo again. And I think only Adrian can put it back. I don't know how it's possible, but why don't you like not look it back? Because we don't have too much time. But this is impossible. Normally you shouldn't do it. You have to take it from the like rigid part. And Adrian always insists he's going to put it back from like the soft connector. So, oh my God. Yeah. Adrian, that's fine. That's fine. Okay. I wanted just to show one more thing. Yeah. Could we? So now, you cannot do the two of them. You cannot talk to two robots at the same time. Ah, the other one not working. Oh, the other robot went to sleep, so. All right, let's upload Adrian, and thank you. Thank you for, okay, let me take this thing. Yeah. Yeah, Adrian said he will fix, wake up the robot, and we'll have other demos later in the day if we have the chance. So imagine how powerful this would be to connect robots remotely and get that interaction with the challenging environments, difficult environment for human. And this is similar to what, now my laptop is not working. Okay, so let's see. Okay, all right. Now it's working again. Yeah. All right, can we continue the projection? All right. So one thing about robotics we often forget is the fact that robotics, I mean, we call robotics everything, but we have to distinguish between robotics for robot moving in free space, and this really relates to mobility, like all kind of motions and navigation challenges, sensing, but it's very, very different from the robotics that deals with physical tasks. And it's really this physical task robotics that is bringing a lot of challenges. So interacting with the physical world requires not only precision, but also requires dexterity, and that is bringing the challenge of sensing and closing the loop and finding ways to interact with those environments. So at Stanford, for many, many years, we've been working on those problems. And there was a project called Romeo and Juliet that was demonstrated at the inauguration of the Gates building. By the way, Juliet was at the museum in Munich for several years. But I like to show you this just to give you an idea about what it means to have compliance. We were able in 1995 to create behavior that are still very difficult today. I mean, vacuuming, ironing, interacting among robots, applying this later to humanoid robots, applying this to human, applying these in ways where we are integrating the musculoskeletal model. All of this came because we really moved away from the modality of controlling robots through trajectories, which was very successful in manufacturing. Because in manufacturing, everything is well defined. We have fixtures, we have jigs, and now we are talking about unstructured environment that requires an abstraction. We cannot go through a programming trajectory again and again because the environment is uncertain. And human managed to do it, and human are not precise, but we compensate by touch and feel. And this is the thing. We don't need anymore the rigid robots, we need the compliant robots. So this is compliance, and compliance leads to strategies, and those strategies are very rich with humans. So manipulation skills can be captured by observing human motion, performing tasks, and you will see that in our laboratories we have this motion capture that take and segment the data. But what we do then, we understand what was going on by looking at the physical model. Interaction between objects is interaction between two compliant frames. And those two compliant frames need to be determined. So we digest the data, and then we have a strategy that allows us to execute motions. So here is a task of cleaning a surface, but at the same time, the surface is moving. And here is a task of placing objects. We are teaching the robot haptically, and then the robot is going to perform this task autonomously. Here we are opening a valve. All of this is done in an architecture of multi-layer system. This is another mistake often that take place when we are dealing with contact. That is, the problem is not just one loop, the connection between perception and action. The physical robot needs to be controlled at kilohertz, but the input is at much slower rate. And the reasoning is at much slower rate. And that means we are building autonomy, but this autonomy is merely functional, navigation, contact, removal of objects, bolting, whatever it is. However, the cognitive autonomy comes from the human, and that's why we need an interface. And that interface can be speech, can be haptics, can be program. And then we can perform those tasks. One important thing in those development is that we developed a platform that allows us to generate all these models, difficult models sometimes, automatically for any robot. The system is called CIFE, and the system is used to control any robot, and developing the system for any new robot takes. So it's really powerful system that build behavior that are almost impossible today because of the feedback, the multi-contact resolutions that we achieve, and the feedback to the different contact locations. These things were implemented and validated on many different robots, but I want to show you how my students use this system in class. So we have the physical robot that is used in experimental robotics. However, during COVID, we couldn't access the lab. So we created a virtual lab. And here the students are developing a project to remove boxes in physical simulation in 3 weeks. Or having a project to prepare lunch. It is amazing, 3 weeks. This is like the 3 weeks at the end of the project in May. And then here is everything is, so the projects varies. There are a lot of projects also in construction, from bolting, painting, and sealing, and many different things. We don't have too much time. Let me just show you this one. This one is very fun, where we are able to see two robots playing together. And this is not animation. This is a physical robot making the contact, estimating where the ball is going to be. In the same way we interact with robot haptically or through human. So what is the secret? You know, there is a problem with teleoperation that when we have delay, the system goes unstable. But what we have done here, this is a demonstration of interaction physically from Stanford to Chengdu, 7,000 miles. So Mikhail is closing his eyes and telling us what he's feeling. So the system relies on this dual proxy concept, where we replace this model with this one. When we are closing the loop, actually we are just not closing a state, we are exchanging input between the robot and the interface. And the inputs are proxies, which means sort of like the goal, the input system, the input goal for the robot or for the haptic device. And this is how we develop the system. In fact, the system becomes autonomous because we can teach the robot how to do a general scan. And here is the robot performing a scan for the pancreas. And then if we detect any problem, then we can connect the robot to the proper healthcare provider. Liver. Another problem during COVID came to be very difficult, wearing all the gears to do a very simple procedure in the hospital, in the ICU. And why don't we just place a haptic device outside? But then you have to make sure that the robot inside is really safe. I mean, 100% safe. The question that we are trying to address is how can we remove physically human from dangerous, difficult, challenging environments, but reconnect their skills to the task. So we're building the next generation of haptic devices that will be even more compact and more efficient. We are building the next generation of human-friendly robots that are much lighter compared to what we have today. They are just amazingly compact, and also they have these characteristics of protection that is separation of workspaces that is reconfigurable, passively reconfigurable. That is, we have a patient, with a camera we do the scanning, and the robot will be reconfigured to become patient-specific robot. That is, we change all the joint limits to make the robot capable of separating the workspace of the robot from the workspace of the human. So there is no danger, even if the computer goes, if the computer fail or a sensor would fail. Well, these probably, I mentioned this last time. I mean, these were a lot of the examples of projects our students work on. And we have been really looking at ways of dealing with those challenging environments that requires maybe even humanoid robot to move because the terrain, but then humanoid would face a lot of problems moving. So we started integrating these poles, we call them suprapeds. And with suprapeds, you are able to increase the support area of the robot, and the robot can now operate in rocky terrain without falling. So it's almost like quadruped now, but this is reconfigurable as needed. We're working with different oil and gas on offshore robotics. Why do we need human to be on those platforms? Can't we place a robot and put human onshore? Most of the human, there will be, of course, a few needed still. We have a project in doing minimally invasive mining, gold mining in Peru, that just goes and focus on what is important and not to remove everything because we are removing human from those environments. We have those haptic devices on the space station, the European Space Station, and we are able now to control robot on the ground from space. There are a lot of challenges in places like CERN in terms of inspection, maintenance, and we are discussing a lot of collaboration with those groups. Now, just a few words about Ocean One. I mean, we couldn't take this robot and turn it into a robot that goes to 1,000 meters. We had to go through a lot of modification of the flota by finding material that can take the pressure, ways of supporting the arms, and a lot of sensors, a lot of modification. We built the robot over the period of COVID, tested it here at Stanford, and then we took it to the Mediterranean, to submarines and places that... So La Ciotat is the location of our boat, and here is the robot going in the water. When this robot goes to the water, it doesn't go alone. It has a lot of other robots supporting the task of putting light and filming and also providing the power. And this is the control room. Again, haptic devices interacting with the robot. So the robot at the Lightning, this is the same aircraft that Saint-Exupéry was flying, and it's at 40 meters at La Ciotat. Le Proté at 124 meters, in Bastia, we went to an area where we have a 2,000-year-old Roman boat, and we recovered some beautiful cups and other artifacts. Here is the view you see when you are operating. You see the archaeologist said, please take this cup, and I'm approaching the cup, and when you move your hand, the water pushes the object away. And it's very, very difficult to take objects, and you have the sediment that start to come. You need to feel and touch in order to get it. And here we have it. Here it is. It's a beautiful cup. Imagine they study this shape from 2,000-year-old pottery in Rome. And finally, we have it in our hand. We brought also oil lamps decorated with palm, another one decorated with mask. In fact, we found the address on the back of the pottery. A lot of shrimp, a lot of life at the depth, and we brought also pieces of wood which tell the story of the boat. And there were a lot of amazing results for the study of marine biology on that particular site. We went later to another boat called the Crispy at 507 meters. And after scanning, we were visiting the boat, and then we went all the way to Cannes from Corsica. And in Cannes, we were visiting this plane we cannot go inside, but we have a camera from outside that we place and we film inside. And then the big challenge, taking the robot all the way to 1,000 meters. So it turned out of Cannes, just on the about 10, 15 minutes from the beach, you can reach this hill that goes down thousands of meters, and we were really scared. I mean, we didn't know if the robot will survive. You build, you design, but you don't know until you test. And the robot kept going and kept going and kept going 850 meters, carrying a message that says, a robot first touch of the deep sea floor, a vast new world for human to explore. And I said, we won the Palme d'Or. So here is the video telling that story in 3 minutes. And the film is too long to show you today. So this is our boat. My students working really hard, preparing the robot hands and equipment. So here you can see how we're touching the Lightning, the P-38, filming this plane. And this is the control room with the haptic device. It's very hard to take something, anything from the seabed. And then you place it. So the Crispy is an amazing site. Crispy, an Italian boat that was shot by the British during the war. And we are putting the camera in here, and we suddenly, the biologist was really surprised to see these iron-eating bacteria inside. And this is how those boats will disappear eventually. A lot of life. And now, finally, the big dive. It's working now. It's always like this. So this was really, really exciting mission because despite the fact that it was COVID, we had to go to these different locations over almost 2 years. We couldn't travel at periods because of COVID, but the results that were, completed in July of 2021 were really, actually 2022 were really amazing. And that is why we have this movie, and the crew is now waiting for us to have the next expedition, which might include some really cool locations. So one thing I wanted to say is we're going to be now luckier exploring this robot, because we are building a new center at Stanford. And this is the Stanford Robotics Center that is just over here in Packer. And this center is really designed to bring a multidisciplinary approach to robotics, to connect robotic research with the real applications, because robotics requires so many different things, from material to sensing to perception to reasoning to design, architecture of control, all of those things. So we are building this critical mass of multidisciplinarity in the center, but we are equipping the space with the latest, most modern equipment, and we are also benefiting from the engagement of industry and partners working with us to create that amazing new space for robotics in the real world. And you can see here everyone. You can even see Martin. And here is Martin. And this is, as I said, in the David Packer building. And the center, I said, because the center has an aquarium. And the aquarium is equipped with the current and waves, so we can really study the problems in more controlled way, and that will let us make much more advances in this area. Here is the concept. The aquarium probably will be finished by the end of the year. So this bridge between robotic and research is going to focus on these 4 areas where the core of research is being applied in field robotics, future of work, education and culture, health and wellness. And all of these are separate efforts that will be conducted in these studios performing a flagship project in all these different areas. The mission is really to enhance human capability, but also extend our reach, at the same time helping the planet. So there is a very nice program where industry is involved in the activities and the development, and our students, our researchers are very excited about this new development for Stanford with all its potential. And I want to tell you that there is a launch very soon coming on November 1st. November 1st to November 3rd, we will be having a big festival of robotics here at Stanford. And I hope we will see those of you who are able to join us. Thank you very much for your attention.
Are you doing another demo?
Just in the background.
Yeah, okay, cool. Yeah.
It is working now. So.
Yeah. Please say your name and the company. Yeah.
This is Keats from Exponent. My question is, what's the biggest uncertainty between the 100-meter and the 1,000-meter environment? Are you able to simulate, the pressure and the condition in a lab environment without going actually in the field and test?
So you're asking about the difference between 100 meters and 1,000 meters
Correct,
environment?
Yeah.
That's the question. Okay, yeah. So the challenge is if we think about first of all, I mean the big challenge with the robotics underwater is water, the pressure. As you go to 1,000 meters, you have 100 times atmospheric pressure. Anything that you take under, like if I take this to the water, this will becomes like a piece of paper. The pressure is huge, 100 times atmospheric pressure. And if we go to 5,000, it's like 500 times. So how we can deal with that? Well, we deal with that by creating a robot that is floating and floater that can support that pressure. And we deal with it by creating arms that has the same pressure inside and outside. And that is by taking the pressure from the water, putting it in a system of springs that presses oil that goes inside the arm. And then now the arm has equalized pressure from outside and inside. Now, as we go deeper and deeper, these solutions requires special material. The material we used finally for flotation is material that is built like glass, but with hollow microspheres. So you have spheres. Spheres are very good to resist pressure, but they are empty inside and very, very strong, but light. And the material that you see on the robot is amazing. I mean, you cannot machine it yourself. You have to special machines, special location that they can do that. And this is the success of robotics today. Robotics is benefiting from these new technologies that are coming to helping robotics, from materials to sensors to computer power to mechatronic integration to all these things. So that is why we see potential machines that are going to be amazing in the coming years because of that convergence of technologies. But the difference between 100 and 1,000 is huge. Thank you. Yeah.
Hi. I was wondering if there is any specific reason why the robot is like shaped like a human when all you need is vision and hands, and why is it not like a fish with hands or something of that sort?
Yeah, why it looks like a mermaid, you mean?
Yeah, I mean, it's almost
It doesn't
human.
look like a humanoid, it looks like a mermaid.
I mean, wouldn't that help with it navigating the waters?
Yeah, this is a very good question. I have this question very often. I mean, why did we build it this way? So actually, the robot is built to provide the ability to an operator to use two hands. We agree we need two hands. But we need to see our hands with respect to the environment. I mean, I'm moving towards something, I need really to see it. So I need, like the cameras to be stereo, to see depth and move. And it turned out like the upper body of the human is amazing. I mean, this is the best design. And then we added the support, how you are moving that part of the body. Well, you need to place the electronics, the sensors and all of that. And it came to be very close to mermaid. Now, it is mermaid, I'm not like just saying mermaid for joking, but truly it is something that we are considering, because using thrusters close to the seabed is very, very difficult. You see, you get all the sediment, and that's why we are considering variation of design. Thank you.
Hi, Lavinia from Stanford, PhD with Martin. I have a few questions. So the first question is, how do you check how do you make fatigue tests on the robot, if you do any? Because maybe the first expedition can be successful, but I was following closely the Titan from OceanGate that imploded, and it was not his first time going down there. So is there a way to assess if the next expedition is not gonna fail.
This Titan was so crazy. I cannot believe. I mean, also, I mean, why human needs to go down and just through a small window to look from, and what are you doing? You're not able to touch, you're not able to perform any task. And this is why ocean, I mean, I get a lot of phone calls after the accident about how can you use this in a situation like this. But also, I mean, in practice, you really need a robot with those capabilities. How we test? In the case there, the problem was they knew about it, and some of the engineers were still now talking about how terrible that was, and the material used under compression and release, compression and release. It took 32 times before the fatigue came and destroyed it. Those systems, first of all, there is no human inside. And those systems are tested. So we tested the arm in our own compression. I mean, we do like to make sure that the oil is not going to go outside. We have facilities to do those tests. But you cannot put the whole system to a test at that pressure, 1,000 meter pressure, without having very, very expensive facilities. We couldn't afford it, we couldn't do it. But, well, we went to the field and we found this space. And it was so exciting to see that the robot really didn't care. I mean, just went down and tested, I mean, performed properly as designed. But testing facilities are very important, and we are looking, to find collaborations in that space. Yeah.
And quickly, is there a reason why you chose that specific end effector arm? Like, it's quite a big arm, so I was wondering why such a big end effector.
Well, we have, you saw another arm, the one like the human arm that was touching the airplane in the beginning. So we can change the arms. It's very just like small interface. You can put any hand up. Sorry, you're talking about the hand, right? Yeah, so we changed different hands, and we are still redesigning the hands. But to carry vases underwater for archaeology, we needed this kind of hands. And this hand is really, really amazing because it's 1 degree of freedom, one motor. It closes, but closes in a specific way. It has magnets and special design and springs. So when you close it, it's closed in a specific way. And also you can feel the amount of pressure you're putting. We have to be very careful not to break anything. These are very valuable. And I saw the archaeologists screaming when they were using their like, they have these heavy robots, they come and like they try to take things and destroy everything. So we are very, very careful. I think.
Phil Bushabi, Commercial Design Group again. I was going to ask, I thought I heard you mention that a lot of the robotics still actually are being used with hydraulic systems. And I know that Boston Dynamics, they came out with their next generation Atlas, and I believe they removed all the hydraulics, so it's all completely electrical. And I would think, especially for deep sea, maybe that might be something better. I don't know. Have you guys thought about that?
Well, Mark Rabert is a good friend, and I follow his work for many, many years. I mean, when he was at CMU, MIT, and then at Boston Dynamics, and he really was more focused on the methodology. So he really used very natural way of like spring-like behavior to get like the hopping robot, if you remember, and all these things. But when he went to hydraulic, I really didn't like it. I mean, I know hydraulic is a very big challenge, especially if you are in environment where you don't want the mess of oil coming and all of that. So basically, I mean, moving toward electrical control is amazing. And this is what I was saying, the progress with technologies that are related to robotics enable this. And this is what is really the future of robotics. I mean, I tell my student, the first 50 years of robotics, we were fighting with the machine rather fixing and advancing the research, because we didn't have the right platforms. We didn't have the right robots. And now this is changing. And this is really the optimism that we have about robotics. So more compact, lighter, safer, not this bulky, heavy, dangerous machine.
Gabor Nagy, Meta. You mentioned that the human body is amazing from the torso up. But you also
the whole human body. I said for manipulation, the upper body is very important, but the human body is amazing in many different ways. And when you come to the center, you will see the human motion compared to robots. How much energy efficient we are. It's amazing. Just how the human body, sorry for it.
No, it's you had a video where, like a robot was struggling on two legs going through debris. And I was wondering, I mean, you're not limited to two legs. You could have multiple legs. But, like it would probably also look quite scary. And usually humans are attached to things like, I mean, we even saw a kiss on that video, right? like someone was kissing the cheek of the robot. So, like, have you done any studies of, like how the shape affects these, human emotions?
By the way, I mean, humanoid robotics or legged robotics, I do not recommend. I personally, I work with them. I know the humanoid, they are the challenge. We work, I mean, you have to balance, and if there is a disturbance, you're going to fall. So this is not very safe, but the technology, we need to study that to advance the technology, because it brings all these different aspects of stability. What we try to do here is the stability, the balance depends on the area of contact with the ground. We increased it with the poles. And now you have huge stability. You're transferring like almost quadruped to biped. And that was a solution I thought about, because I'm always concerned about safety and balance, and especially if you want to use it in unstructured environment. In any case, has been really a pleasure interacting with you and talking about exciting things like this robot. Thank you again very much for your attention.